You know that feeling, right? When you're playing with magnets, that weird, invisible push or pull? It's like something out of a sci-fi movie, a force that can move things without even touching them. It feels like pure magic, but it's not. It's physics, and it's one of the most fundamental forces in the entire universe.
So let's get right into it. We're going to pull back the curtain on this incredible invisible power. We'll figure out what magnetism really is, where it comes from, and why it's so unbelievably important for all of us here on this planet.
All right, the secret to this whole thing is something called a magnetic field. The easiest way to think about it is like an invisible bubble of power that surrounds every single magnet. And if another magnetic object wanders into that bubble, it's going to feel the force. The deeper it goes, the stronger that force gets. This field, this is the invisible stage where all the action happens.
Okay, so we've got this magnetic field, but how does it work? What makes it tick? Well, like any good game, it's all about the rules. And honestly, the rules of magnetism are super simple, but they are also incredibly powerful. So, rule number 1. Every single magnet, and I mean every magnet, has two different ends. We call them poles. You've got a north pole and a south pole. These are basically the power centers of the magnet, and you will always find them in pairs. Doesn't matter how big or small the magnet is. And this next one, this is the golden rule, the one rule to rule them all. It's this: like poles repel and unlike poles attract. So, a north and another north, they're going to push each other away. Same for two souths. But bring a north pole near a south pole, they'll snap right together. They attract. Seriously, that's pretty much the core of it.
We can actually see this invisible force, in a way. We draw these things called magnetic field lines. And when you put opposite poles together, you can see the lines reaching out, connecting, just pulling those magnets into an embrace. But when you try to force two of the same poles together, whoa, those lines bend and swerve away from each other, pushing them apart. It's like we're finally getting a peek behind the curtain at that invisible push and pull.
So, what if you try to break the rules? What if you say, I'm just going to have a north pole all by itself, and you snap a magnet in half? Well, tough luck. The universe says no. The second you break it, you don't get a lone north pole. Nope. You get two new, perfectly formed little magnets, each with its own north and south pole. It's impossible to isolate just one. You can never, ever have a magnetic monopole.
Okay, so we've got the external rules down. We know how magnets act, but now we're going to go deeper. Let's talk about the real secret. What's happening on the inside? What makes something magnetic to begin with?
Let's frame it with a really simple question. You can take a regular iron needle or a paper clip and turn it into a magnet, right? But have you ever tried doing that with, say, a plastic spoon or a wooden block? It just doesn't work. So why? What's the difference? The answer, my friends, is hiding at the microscopic level.
It all boils down to one thing: chaos versus order. Inside something non-magnetic, like that plastic ball, the tiny little magnetic fields of all its atoms are just a total jumbled mess. They're pointing every which way, and they all just cancel each other out. But inside a piece of iron, it's a whole different story. The atoms get organized. They form these tiny, neat little neighborhoods where everybody's magnetic field points in the same direction. These neighborhoods have a name: magnetic domains.
So what exactly are these domains? Well, imagine these microscopic little zones where literally billions of atoms have all decided to team up. They all point their tiny little magnetic fields in the exact same direction. You can almost think of them as mini magnets that are already baked into the material, just waiting for instructions.
And this is the secret sauce to making a magnet. See, in a normal piece of iron, those domains are all there, but they're pointing all over the place, totally random. All their forces cancel out. But if you bring a powerful magnet close by, it's like a drill sergeant shouting orders. It convinces all those little domains to snap into formation and point the same way. Once most of them are aligned, all their little magnetic forces add up into one big one, and bam, you've just made yourself a magnet.
Now, here's the key takeaway. Not everything has this internal structure. It's only a few special materials. We're talking iron, nickel, cobalt, and a few others. These guys are called ferromagnetic materials, and they are the only ones that have what it takes to become a strong, permanent magnet. Okay, so we've gone from the big picture down to the microscopic. Now let's scale it all the way back up again. I mean, way, way up. We're going to go from these tiny little domains to the single biggest, most important magnet in all of our lives: planet Earth.
You all know what this is, right? A compass. It's such a simple, yet totally brilliant piece of ancient tech.
All it is really is a tiny little magnet that's free to spin around. And for hundreds of years, it's helped people find their way by always reliably pointing in the same direction. But what is it pointing to?
I mean, that little needle is just doing what magnets do. It's responding to a magnetic field, but it's not picking up on your fridge magnet. No. It's lining itself up with something massive, something that covers the entire planet.
And there it is. Our entire planet is a giant magnet. Deep down in its core, you've got this churning, swirling liquid iron and nickel. It acts like a massive cosmic generator, a dynamo, creating this huge magnetic field that wraps around the whole Earth. So that compass needle is just a tiny magnet playing follow the leader with our planet's gigantic magnetic field.
But check this out, because here's a fun little mind bender that proves that old rule, opposites attract. The tip of the compass needle that points north, we call it the north-seeking pole, right? Well, for it to be attracted to the geographic North Pole, that place has to be its magnetic opposite. So get this, the place we call the North Pole is actually the Earth's magnetic South Pole. Wild, right?
Okay, so this giant planetary magnet isn't just for navigation. It's so much more than that. In fact, you could argue it's one of the main reasons any of us are here at all. It's our planet's invisible, life-saving shield. So the sun, it's not just sending us light and heat. It's constantly firing off this stream of super high-energy particles called the solar wind. It's basically a storm of radiation. And as this dangerous stuff comes screaming towards us, our magnetic field, we call it the magnetosphere, steps in. It acts like a force field in a sci-fi movie, deflecting that storm and steering it safely around us.
And let me be super clear about this. Without that shield, we'd be toast. That solar wind would literally strip our atmosphere away, boil our oceans dry, and just bombard the surface with lethal radiation. This magnetic field isn't just cool science. It is quite literally a lifesaver for the entire planet. And you know what? This shield has a beautiful side effect. Some of those solar particles get caught in our magnetic field and get funneled down toward the poles. And when they slam into the gases in our atmosphere, they light up. They create that breathtaking celestial light show we call the aurora, the northern and southern lights. It's just a stunning reminder of that invisible shield doing its job. And that brings me to one last, pretty mind-blowing thought. The geologic record tells us that every few 100,000 years or so, the Earth's magnetic poles just flip. North becomes south, south becomes north, and while that's happening, the field gets super weak. So here's the question I want to leave you with. What happens to our shield and to everything living under it the next time our planet's giant magnet decides to flip the switch?